Yeah, so welcome to the last session. Today will be the 12th week. So, so this will be the last session, tutorial session. And along with that, this Wednesday, 16th of April, I am planning to take one extra session where we can discuss any topic from whichever topics we covered so far. We can discuss. If you have any doubt, you have any, uh, if you want to understand any concept in a better way or more elaborately, so I will be taking one extra session. If you want to join, you may join on in the same time from 6 p.m. on 16th. Okay. So, and if you have any particular topic you want to discuss, like you can tell me right now only. If you have any topic in mind that you want me to discuss, you can tell me, or otherwise we will discuss that day, like portions of all the topics, some portions. Okay. So, yeah. So today's topic of discussion is closed loop control. Closed loop control of DC-DC converters, and also sine pulse width modulation SPWM of single phase inverter. So yeah, this is another practical aspect that you will require when you will run a hardware, right? So after designing the circuit, selecting all the components, the devices, the passive components, everything. At last, when you will run the circuit, you can run it in open loop, but you will have to run it in closed loop also. Because unless you run it in closed loop, you can't regulate the output voltage or output current, right? So you will have to run it in closed loop. So what is closed loop control? Why should we do it? How to implement it? And what are the challenges while implementing the closed loop control? And what is pulse width modulation? Specifically, sine pulse width modulation, sinusoidal pulse width modulation in a single phase inverter that we shall see today. So basically, the basic structure is something like this. So suppose you have this buck converter, and this structure is applicable for any converter, boost converter, buck boost converter, or for isolated converter as well. So the basic structure will remain same for any kind of converter. So here we have this BJT, which is a control switch, and we need to send some pulses. Pulses in the sense, for BJT, we need to send some base current. And if it would have been a MOSFET or an IGBT, then we shall send gate to source pulses, right? So you need to have some pulses here. Now, in order to have the you can give those pulses at a particular duty, right? You can fix a certain duty ratio, suppose 0.4, and you can generate the pulses. Or if you want to implement closed loop, then you will have to make this structure. So first of all, here there is some sensing circuit. The sensing circuit is required so that suppose you want to regulate the output voltage, then you will sense the output voltage, and then you will step it down via resistive divider or some kind of circuit that will attenuate it, and you will pass it through the sensing circuit, right? So in the sensing circuit, basically there are some filters, and there are also some attenuators that will step down the actual voltage, and this sensed voltage we will give feedback here. So this is the feedback. Here you have the reference VOREF, which is the reference voltage that you want to maintain. And here you are giving feedback, right? Because this is coming at the negative sign. This is called a negative feedback. So if you are giving the feedback here, now there here you get some error. So this plus and this minus, after subtracting this actual signal, you get some error here. What is your objective? Your objective is to minimize this error, or the best case will be you can if you can make this error completely zero, right? That will be the best case. So to make this error zero, there are some blocks which we usually say the controllers, right? So there are different types of controllers. There are proportional controllers. There are proportional integral controllers. So they are the most commonly used controllers, PI controllers we say. But there are also higher order controllers, right? PI controller with a roll with a rollover pole, right, which will again attenuate the high frequency signal. And there are some higher order controllers as well, but we will not discuss them. We will only discuss PI controller here, right? So after this controller, this signal, this there is some control signal that is produced here, VC suppose, and this control signal we compare with a triangular carrier, right? So this part is similar for every controller, every structure. There will be some control signal VC, and there will be a carrier wave whose frequency is very high, right? For DC-DC converter, uh, this the frequency of the carrier wave is basically your switching frequency, right? That is usually your switching frequency. So you compare it. The logic is, suppose this is your so suppose this is your carrier wave like this, and this is your control signal. So the logic is, when your control signal is greater than your carrier signal, then the output will be high. And in the opposite case, when your reference signal is lower than your carrier signal, then your this output will be low. That is the logic. So if you see at this intersection positions, in these positions, so from here to here, the control signal is higher than the carrier signal. So here you will get high pulse, right? So here you will get high. Then again you will get low for this duration when this carrier signal is higher than your control signal. Then again after this you get a high signal because it is again becoming lower than your carrier signal. Sorry, lower than your control signal, right? So like this you will get the pulses, right? This is the logic. And then
Carrier signal means information signal.
can you say, you are not audible. Can you say it louder?
Carrier signal means information signal.
Carrier signal means this kind of a triangular signal. This is called the carrier.
So information signal means.
Information, see, the main information will be this control signal. And this carrier signal is basically a recurring signal. So whatever control voltage is produced, that will get, so your main signal is this. So based on the controller action, you will get this control output, right? So depending on how much is the error, how much you want to compensate, based on that, this control signal will be generated. And this signal doesn't get changed. It is always the same. It is just a recurring signal with a fixed frequency like this. So there is no change in this. The only change that occurs is in the control signal. So if the level of this control signal goes up or goes down, based on that, your pulse pattern will change. So this is the control. That's why this is called the control signal, right? And this is just the carrier signal. So I don't think you can say that this is information or something. This is just a signal that we used for comparing it with the control signal to generate the pulses. So based on the level of this control signal, whether it is at this position or it is here or it is at a lower position, your pulse will change, right? Because you can see the intersection point is changing. The intersection point with the carrier signal is changing based on the control signal. So that's how we would get pulses changes. So so this is called pulse width modulation basically, this process. After that, we have the gate drive signal. So we have already seen what does the gate drive circuit do. So from here, we get the actual pulses that we will feed to our switch, right? So we get some pulses that we will feed to our switch, right? So if suppose your output voltage is greater than or less than your reference, based on whether the error is positive or negative, the controller will take proper action so that this error gets minimized or it is very close to zero. And then it based on that control action, your duty also gets changed. Duty means the ratio, uh, of the switch on duration to the total time period. So based on this control signal, your duty will change. If suppose your voltage, if this is a buck converter, right? So the relation is V out is equal to dV in, right? This is the steady state equation. V out equal to dV in. So if your V out suppose increases due to some disturbance, then your D has to, if Vi is constant, but your V0 increases from its reference value, then controller will take an action so that your duty reduces and your V out comes to that same value, to the reference value. Similarly, if your V out value decreases due to some external disturbance, then you will have to increase your duty so that the output voltage again comes back to its reference. Okay. So this is what the controller performs.
Why we need closed loop?
Sorry.
And why do we need closed loop?
Otherwise, how will you control the output voltage? So suppose there are different noises, external disturbances. So suppose you want to maintain the output voltage at a particular value, suppose some 15 volt, but due to some external disturbance, it is it changes, right? So how will you control that? If you operate it in open loop at a fixed duty, so how will you, even if it from 15 volt, if it decreases to 14 volt suppose, then how will you change that? You can't always manually do that, right? So each time you can't manually change the duty. So some action needs to be some there should be someone who will take care of these changes, who will take care that whatever be the external disturbance, you always maintain this voltage at a particular level. So that's why you require this closed loop control. Yeah. So so basically now what we need to see is what will be this K? What is this K? What will be this controller? Right? And how does it work? That we need to see. Now, if we are talking about DC-DC converters, so at steady state, your output is DC, right? Your output is a DC value. So you should ensure that in steady state your output voltage is exactly following this reference, right? There is no steady state error. So in steady state, if there is some error, that we call the steady state error. Suppose this is your reference, and after your controller settles, your system settles down, you get an output voltage something like this. So there is always some gap which is fixed gap. So this error is called we call it as the steady state error. So we should, first of all, we will ensure that there is no steady state error. Along with that, we will also have to ensure that this section, this we call the transient portion, right? This we call the transient. Transient means the voltage has still not reached its steady state, right? The system has not reached its steady state. So this transient performance we will also have to improve, right? Like it shouldn't be very slow. The system shouldn't be very slow. Like it is going like this, and then after very long time it is settling like this. It shouldn't be like this, okay? And it also shouldn't be like this that it has a very high overshoot and then after some damping it is settling like this. So we will have to improve this transient action also and this steady state performance also. So let's see what kind of controller we need. See here, if you see, so suppose this k is some constant, right? This is a simple constant, some constant value, some 1, 2, 3, or some value, right? So what it will do is basically, if this is a constant, then your uh, your frequency response will look something like this. So here it will keep on increasing, and at high frequency region, okay, it will have a very high gain. So this is basically expressed in logarithmic scale. So this is 20 log 10k here. This is the gain and this is the frequency in omega. So this will be the frequency response. So you see at high frequency region, the gain is very high, right? We don't want that. Why? Because then your unwanted noises will get amplified. This region, these signals, we don't want amplification, right? These signals we don't, because we want only the DC part. We don't want any unwanted noise. But in this portion, you will get only the noises, unwanted noises with very high amplification. So you can't really use a simple constant gain for compensating the errors. Okay, that is not possible. Then you will not get any productive voltage. You will not get any voltage that is useful. You will only get noise. Maybe there will be DC, but over that you will get very high noise, like something like this. So this voltage will be of no use. You can't use this anywhere. That's why we need to use some other type of controller. That's when that's where we will see the advantage of a proportional integral controller. So this is a very simple controller, but it is the most widely used controller. Okay, this is very popular. So yeah, so if you see here again, we have the gain in the y-axis, and we have in log scale, and we have the frequency in the x-axis, right? Now, suppose we want this kind of a frequency response. So this is good, right? Why? Because here, if you see, when this frequency is very low, that is, the signal is almost DC in this region. here you are getting a very high gain, right? The gain is high. And as the frequency is increasing, your gain is decreasing like this. And after this point, it is here it is 0, and then it is going to negative, right? So the signal is getting attenuated at higher frequency region, right? So this is getting attenuated, right? So this is a good response, better than the previous one, because it is giving us what we want. At DC, it is giving us high gain, and at high frequency region, it is giving attenuation. What kind of controller gives us this kind of frequency response? That is the integrator. So you guys know Fourier response, then Laplace transform, all these things. Do you guys
Yes,
know?
ma'am.
Okay, okay. So basically, so the Laplace transform of an integrator gives you this 1 by s. This is the Laplace form of an integrator. So if you plot this, you will get this kind of response, right? So what this means, that at omega is equal to 0, so this is some finite omega, basically suppose some 0.1 rad per second, like this. So at omega is equal to 0, this gives infinite gain. That's why at steady state we can have zero steady state error if we use an integrator, right? So this keeps on increasing and increasing, and then at omega is equal to 0, we will see we get, like, ideally, of course practically we can't see that, but practically we will get very high gain at DC, at steady state. Okay, so that is the advantage. And another advantage is at high frequency you will get attenuation. So this is Ki, and instead of 1 by S, you can use some constant Ki, right? So based on this Ki value, you will get similar lines in parallel with this one, but with higher bandwidth or lower bandwidth. So this is the bandwidth. So you can have lower bandwidth ones, like this is the so the bandwidth is smaller, right? From here to here. Then it is slightly increasing, right? Then it is here. And you can also higher bandwidth ones, like this, like this. So you can have a set of parallel lines based on Ki values, right? So this portion. So Ki and then one integrator. This is the integral controller, right? So then you will ask that, okay, now this is sufficient. So here we are getting high gain, here we are getting attenuation, then our work is done. But no, there is another problem. The another problem is the transient performance. So the steady state performance, we have ensured that we will have good steady state performance, because at DC we are getting very high gain. But what about the transient? So if you have this kind of response, then your transient response is very slow. It will be like this. So what you can do is, here we can have a proportional gain as well, Kp, right? And then we can add them here. We can add these two and we can get a proportional integral controller. Okay, proportional integral controller, like this. So these two will get added and you will get Kp plus Ki by S. That is our proportional integral controller. Okay. So if we add a proportional like Kp here, what will happen is the transient will be something like this, and then it will settle. Okay. So your settling time will be lower, and your transient performance will improve. So then the frequency response will not be like this. Then it will come here and then it will get flattened out, right? Because you can see we are adding 1 0. If you again simplify it, kp plus ki by s, so it will be, take kp by s common. If you take kp by s common, then you will get s here plus ki by kp, right? Ki by kp. So this is basically a 0, right? S plus, so at minus ki by kp, so at this point, you are introducing a 0. What is this point? This point is ki by kp. Ki by kp. So after it was decreasing with a slope of minus 20 dB per decade, here, here it was reducing with the slope of minus 20 dB per decade, but then you introduced 1 0. That's why from minus 20 dB the slope became 0 and it got flattened out, right? So this is the PI controller. Sometimes we also use controllers where like uh, like here it is going right like this, and then we again introduce another pole at very high frequency, suppose in the vicinity of the switching frequency, so that again there is minus 20 dB per decade slope, so that here at in this switching frequency region we get attenuation. But yeah, like that is another case. So for now, you you see that it comes like this at minus 20 dB, then it becomes flat like this. Okay. Yeah, so that's what is written here again. So we add the Kp, the proportional gain for improvement of transient performance, and Ki of the takes care of the steady state performance. Okay. Yeah. So basically another strategy to improve the control action is to add feed forward term. What is feed forward term? That we will see. So suppose here we have taken one example. So suppose buck converter only, right? So the buck converter, if you plot V out versus D, then this is a linear relation, right? Because V out is D times V. So this slope is V input, right? This is a straight line passing through 0. Now suppose this is your operating point. So suppose this is your operating point. You were operating at this, and due to some disturbance, there is a variation around this steady state operating point like this, right? So it can be lesser than that, it can be higher than that, and based on this perturbation, there will be some change in output voltage, and there will be, according to that, you there will be some change in duty, right? So if there is some change in the output voltage, you will have to control the duty so that it again comes back to its previous state. Okay. Suppose the perturbation is d cap or d tilde, and this the perturbation in the output is v naught cap, right? So if we can do something like this, so the controller will only take care of this perturbed part, and the steady state part we will feed it to directly. Then the controller will have to do very less work. So what I am trying to say is that what we will do is we will feed this steady state duty directly here as this positive feedback, like, so because we know we will know from calculation what will be the steady state duty, right? We will already know. So if we know this much output voltage we require, and we also know our input voltage, we will know what will be our steady state D, right? And we can directly feed it here. Uh, sorry. We can directly feed it here so that the controller will only have to take care of these small disturbances. It will not have to generate this total D, right? So then the controller burden will reduce and the overall closed loop performance will increase. Okay. So this is called a feed forward term because we are feeding it, right? We are feeding it to the controller. So this is another strategy by so you can reduce the controller burden by applying this feed forward term. Okay. So yeah, you understood, right? Okay. So let's see. So here it has been what they have shown is suppose what nowadays you know that like EV electric vehicle charging, for electric vehicle charging we usually use a DC-DC converter, right? So actually if we talk about onboard chargers, then usually it may be single phase, it may be three phase. So there will be the grid, AC grid. After the AC grid, there will be one rectifier and PFC stage. Rectifier and PFC stage, right? So that will maintain the grid current quality. And then after that, we have a DC-DC stage usually, okay? And that is usually an isolated DC-DC converter. But anyway, right now we will not go into that. So there will be one isolated DC-DC converter. That is the configuration of a practical onboard charger. Okay. So this will be a DC-DC stage. And after this DC-DC stage, we will have the battery connected with the output of the DC-DC converter. Okay. So we will have the battery here. Right. And this is our AC input. Okay. So for battery chargers, what we need to do is we need to control this current, right? The current that is that the battery draws. So the current that will enter the battery, this current we need to control, right? So there is the requirement of controlling so this current is basically the output current of the DC-DC converter. So we will have to control this current, right? Now the output current control, the only way to like control this current is to control the inductor current. So usually for the DC-DC converters, we control the inductor current to control this output current. Okay. For buck converter, the average of inductor current is same as output current, right? For buck converter, if you see the average current through the inductor is same as the average as the output current, because through the capacitor only the ripple portion goes. So the average here and average here, they are basically the same. But for buck boost converters, the inductor current and the output currents, they are not same, but we can indirectly control, right? So this source here, this may be some PV cell, some fuel cell, right? Photovoltaic cell or fuel cell, anything. This source could be. And we will do the current control, and to do that we will regulate the duty ratio, right? That is our control parameter, the duty ratio, right? So yeah, let's see how we can do this. So again, we have taken the example of a buck converter. Okay. So here we have a photovoltaic cell, and then we have a BJT here, then this inductor, and then we have battery here. Okay. Or there may be some other load also. Anyway, so here like this. So there are different types of controls for a DC-DC converter. There are peak current mode control. There is average current control. There are different types of controls that you will eventually learn. But here, whatever is discussed in this course, that I will discuss. But there are several other methods. Okay. See the circuit here. So here, what they have done is, first of all, we have this IL reference current. This is the current reference over here. And we are obviously giving some feedback from the sensed current here. We are measuring this current, right? We are measuring this current, and we are giving feedback over here. Okay. We are giving feedback over here via sensing circuit. There will be some sensing circuit. Okay. And then this output of this, the error is connected here in an op amp, and the positive terminal is grounded, and the output of the op amp is connected to a SR latch. So this is connected to the reset pin, and the set pin is connected to a clock. Okay, so this is the clock, and the output here is connected to the base here. The clock is a pulse of something like this. So this is the time period. This is the time period of the DC-DC converter. This is the reciprocal of the switching frequency. So at the starting of each time period, this clock pulses come, which are very narrow. Okay, so these are very narrow pulses, and like this the clock comes. Okay. Now let's see what happens. So one cycle is shown here, one complete cycle here we have shown. So suppose at the starting of a new period, this clock pulse comes. When this clock pulse comes, it goes to the set pin, and this sets the SR latch, and you get high output here, right? So your output is high now. So then the switch is on, right? The switch is on. And whenever the switch is on, the buck converter switch is on, you know that the inductor current will rise, because here your voltage will be V in, and here it will be V out. So the slope will be V in minus V out by L, that we have already studied. So the current starts rising like this with a positive slope, right? The moment this current hits this limit, which is basically your IL reference, the peak value basically, the moment it hits this, and it goes slightly above this reference, suppose very slightly above this reference, then this error, right? So this error becomes negative, right? Because this actual IL is slightly higher than your reference. Now, if this error is negative, we are feeding this to the negative terminal, so it becomes positive. Okay. And then here the reset pin is high then, right? The reset pin is high. And in that case, what will happen? This output will come, the output will become low. The SR latch output will become low because now the reset is high. So then again, there is no gate pulse to the switch, and then your current will start dropping. Why? Because now the switch is off. Now the inductor will current will free will like this. So the current will start dropping, and when it will again start rising, when in the next cycle again this clock comes. Again this clock pulse comes, and again the switch becomes high, the pulse becomes high, then again the current will start rising. Okay, that is the operating principle. So this is Q, right? So this is Q. Here it becomes 0. Again, when the clock comes, Q becomes high like this. Okay.
And the
Yeah.
duty cycle of the clock is very is 70%, 80% by.
The duty cycle of the
Of the clock is less, it seems.
yeah the clock uh, width pulse width is very low, because you don't need the clock to be high throughout the, this is just a synchronizing pulse. So whenever this SR latch sees, okay, my clock, so the so Q becomes high at the rising edge of this clock pulse. So if your clock is it may be on rising edge, it may be on falling edge also. So suppose in this rising edge it sees that, okay, we have this rising edge, so now I can make my Q high. Okay, so at this portion your Q becomes high. So the clock doesn't need to be high throughout the time period. It is just like a synchronizing signal. So it will just tell you that, okay, when to become high and when to become low. Okay, that's it. So you have, I think you should have, I think you have, have you studied this SR latch? Then your this digital electronics, have you learned all this SR latch, and there are D flip flop, SR flip flop, all these things.
Yes,
Okay,
ma'am.
uh,
And why SR latch is used only? Why not D flip flop?
I don't know. Actually, nowadays we don't really. I don't know. Like usually we use a DSP board, right? Digital signal processor. So initially this SR latch, all this structure was used, but nowadays these structures we actually code whatever we need, whatever like will be the kind of signal that we code in a DSP, right? And then we use it. So you investigate it and tell me how, why we are not using a D flip flop. Okay. I am also not sure, because I have not used this kind of circuitry for my thing. I use a DSP, right? And I code there uh, the all the things.
Okay,
So
ma'am.
yeah. So maybe I am not sure. Maybe here you have to reset it also, right? You can't really make it like the current shouldn't be increasing like this throughout the time period. It will have to reach the peak and again it will have to reset. So that's why maybe the SR latch we use, because you have the set pin as well as the reset pin over here. Okay. So that I will have to see. But yeah. Okay. So you understood, right? How we are doing this, that much you understood, right? How this is done. Okay. So basically, there is an issue that happens if your duty becomes greater than zero point 0.5. If your duty ratio becomes 0.5, then there is some issue in current control. Okay. So see here, two cases we have shown. So for case one, this is case one. Here your duty is less than zero point 0.5. Okay. Your duty is less than zero point 0.5. And case two is when your duty is greater than zero point 0.5. Now here if you see, if due to some external disturbance, your original current should have been like this. It is rising and then it is falling, and this level and this level at steady state they should be same for flux balancing, right? So this one and this level they should be same in steady state. But suppose due to some disturbance the current has some DC shift and it comes here, the operating point shifts here, and it start rising from this point, and it rises with the same slope and it ends up here, right? So then it will come here, and then eventually, although here the operating point shifts, eventually it will coincide with the actual waveform, the ideal waveform, okay? Although there are some mismatch here, but eventually they will coincide. But if in the case of d greater than zero point 0.5, what happens is, again if there is some DC shift here, so you see the current rises, and then here it hits the limit, here it hits the limit and then it drops. But when it can't drop, like it hasn't dropped to this level, right, where it started, it hasn't dropped. But again the clock comes, again it starts rising, okay? And then again here it hits the limit and it starts falling like this. So like this the current will become, it will become unstable, okay, unstable, sorry. So it will become unstable like this for d greater than zero point 0.5. So to resolve this issue, what is done is, instead of giving a constant tie reference, this kind of sawtooth tie reference we give, okay? This kind of sawtooth tie reference. Then what is the advantage? You see here, although this becomes like this, but here within one cycle it will coincide with the ideal waveform. Earlier case it was not being able to coincide with the ideal waveform because it was getting worse and worse with every cycle. But here in this case, so in this case you see, although it starts here, but it can uh, coincide with the ideal waveform because we have changed this current reference. Now this is not, the current reference is not a constant line. This is like this. The current reference is like this. Okay. So it hits the current limit here instead of here. It hits it here, then it comes back. Again it starts rising and then it comes back here. So now the current is okay, right? So like this, you can resolve this issue of instability. Okay. So the implementation of this slope compensated current has we have shown here. Okay. So how you can give this kind of reference? So here we have this current source. Here we have the capacitor, and here we have a switch. Okay. So this inductor current IL is basically VB by L dt, right? So if we just draw it, so here we have the inductor of the buck converter, and then here we have, suppose the we have the battery. Okay, we you have the battery. So basically, when the inductor current is freewheeling, during this negative slope I am talking about, during these positions, during the falling slope here, okay? So during this portion the voltage across the inductor is minus V out, right? V out is here the battery voltage, so V battery by L dt, that is the inductor current. So the slope is VB by L, right? The current slope is VB by L. Now, if you can arrange this kind of thing where you have a current source over here, and then you have a capacitor and a switch like this. So The switch, why do we need this switch, that I will tell. First of all, you see the current, this is like this, and what is the voltage across this capacitor? It is 1 by CS IDT, right? Because we know the current through a capacitor IC is uh, so the current through a capacitor IC is basically C dV by dt. C dV by dt. So if you want to find out the voltage, what will be the voltage across a capacitor? That will be I integral I dt 1 by C. So here this I is a constant current source. So I comes out I by CS integral dt. So if you compare this one and this one, if you compare this one and this one, then you will get I value as VB by L and this CS, okay, into CS, okay. We are just comparing these two, this one and this one, okay, this one and this one. So here, so from this voltage across this capacitor, you will get an idea what will be your current, okay. That's what it represents. So based on the because capacitor voltage is a measurable one, right? You can measure the voltage across the capacitor. So from the voltage across this capacitor, you can get an idea of how, like how to fix the value of your IL reference, okay? And because if you don't have, but you will have to reset this, right? Otherwise, it will keep on increasing like this, like this. But you will have to reset it here. So for resetting this, we have this switch. So if you turn this switch on, the capacitor will discharge, okay? And this comes down to 0. And again, it starts rising. So for resetting this voltage, you for discharging the capacitor voltage, you need this switch. So you may add a series impedance here to limit the current here. There may be some series impedance here. Okay. Yeah. So yeah, this is the implementation. So instead of giving the constant reference, now we are giving this kind of reference. The other things are more or less same. Okay. So So I will take one 5 minute break now, and I will just discuss this pulse width modulation in the single phase inverter, and then I shall start the numericals. Okay. So at 7 we shall start again.
Okay, ma'am.
Okay. Thanks. Let's resume our discussion. So the next topic that we shall discuss today is sine pulse width modulation, or we abbreviate it as SPWM. Okay, this is a very popular technique for inverters, sinusoidal pulse width modulation. Okay, SPWM. Some of you may have also already uh, read this somewhere, or you may have heard of this term, SPWM. Okay. So here the suppose we have this kind of circuit, right? So this is an in single phase inverter. Okay, this is a single phase inverter where where we have two half bridges. This is one half bridge. So this is one. This portion is one half bridge, and this is another half bridge. Okay. So this is a full bridge circuit, and this is a single phase inverter. Okay. How we shall operate this? Now, there are actually, it has not been discussed in the course, but there are also square wave modulation. Okay, so square wave like this. But the problem with square wave modulation is that you get a lot of low frequency harmonics. So due to that, the THD and the filter design, the THD becomes very high, total harmonic distortion. And filter design is also very difficult because of low frequency harmonics. Okay. So basically, what is SPWM? What is square wave modulation? Is basically, I already told you that the method is same. What is the method? The method is that there will be one carrier wave, a triangular wave like this, or it may also be a sawtooth wave. And we will compare the carrier wave with some reference signal, right? For DC-DC
Excuse
converter,
me, ma'am.
yes.
Ma'am, what does low frequency harmonics means?
So basically, what ideally what you want for an inverter, what is an inverter? First of all, the inverter is your input will be DC quantity, and at the output you will get AC quantity. Okay, that is called an inverter. So for rectifier, you saw that in the output we had AC voltage, AC current, and at the output you were getting DC voltage and DC current, right? So the inverter is kind of opposite of that. In the input you have sorry, in the input you have a DC source, and at the output at across the load you will get an AC voltage and AC current. Okay, that is an inverter. So ideally what you want is you want a fundamental sine wave, right? So you want, suppose for us, we want a 50 hertz, we want a 50 hertz sine wave, or for some other countries, they will want 60 hertz sine wave. Okay. Now, how to generate this sine wave? So, so the low frequency harmonics means if you, so what I was discussing is suppose you have this carrier wave. Okay. So you have this carrier wave. Uh, just a minute. So you have this carrier wave whose frequency is very high compared to the fundamental 50 hertz waveform. So it has some frequency in the kilohertz, some a few kilohertz, maybe 10 kilohertz or 20 kilohertz or 50 kilohertz. And you have this reference waveform. Now this reference waveform can be a sine wave. This reference waveform can also be a square wave. Okay. This can also be a square wave. So for when you do the square wave operation, actually, then you don't have this carrier also. What you will do is, so for a square wave operation, the operation is very simple. So you have these diagonal switches. So suppose in the positive half, suppose these two switches will be on, you will 50% duty. That is the simplest thing. You will give 50% duty to Q1 and Q4. Okay. So so the current will flow through this switch like this, okay, and then back. So you will get a voltage polarity like this, and then in the negative half, in the rest of the 50% duration, you will operate these two switches, this one Q3 and Q2. Okay. At that time, these two switches will be off and these two switches will be on, and then the current will flow through like this, and your voltage polarity will change. That is square wave operation. Okay. So so at the output you will get square wave like this. So this is not pulse width modulation, because you are giving fixed duty to the switches, right? You are giving fixed duty, 50% duty to each switch. You will get an output something like this, where this is VCC, right? This is VCC. This is VCC and this is minus VCC. So if you do the Fourier analysis of the square wave, you will see that you will get all the low frequency harmonics, right? So you will get the fifth harmonic, seventh harmonic, all these things. Okay. So if you want a sine wave, the fundamental, so there will be one fundamental, right? There will be one fundamental sine, and over that there will be some higher order harmonics. That's how we get the square, right? So filtering out those harmonics is very difficult. Filtering out the third harmonic, fifth harmonic, because then your filter size will be huge. Your filter size will be so large that it will not be a practical design anymore. That's why we adopt the sine pulse width modulation. Why? Because in that case you see your in that case you operate the switches at a very high frequency. Okay. So that's why if I will explain the operation, then you will understand it in better. What we do is, so there is a obviously a carrier wave that I told you, and and the frequency of the carrier wave is the switching frequency, right? So this is very high in kilohertz, and here you have your reference sinusoidal wave here. Okay. This is what you want. This is your
Excuse me,
ideal
ma'am.
wave that you want. Yeah.
Gode, can you switch off your mic, please?
I'm sorry.
Okay.
Yeah.
Yeah. So basically you have this carrier wave and you have your reference signal like this, the sine wave. Okay. Now the same logic you apply when this reference signal is greater than your triangular wave, then your pulse is high. Okay. So suppose this is for this leg. So your pulse is high, and then when your triangular wave is higher than your reference signal, your pulse is low. Like this, you follow this logic, okay? And this low side switch will have the complementary signal, complementary to this one, okay? So this is for your suppose this leg, and for the another leg you have a reference signal which is 180-degree phase shifted to the first one. So this red one, this is 180-degree phase shifted to this blue reference signal, right? But this is also a sine wave. So here also you put the same logic. When this signal is higher than this one, the pulse is high, and for this one it will be just the complementary, right? For this low side signal. So that's how you get the signal pulses for these four switches. And if you want the voltage across the load VAB, then what you will get a voltage something like this. When Q1 is on, you see VCC comes here, right? VCC comes here, and so suppose here you see this instant here, this switch has pulse high, then again B is also pulse high, right? So B is B leg this one. So this switch and this switch, both these switches are on. So here also VCC comes and here also VCC. The net voltage is 0. Here it is 0. Then at the next interval here, this pulse is high, so this switch is on, and obviously this is off. If this is on, this will be off. And this, the pulse of this switch is also low, right? So this is low and this is high. So this is the voltage then. That's why now the voltage across the load is VCC, right? So this is VCC. If you follow the logic throughout this, you will get a voltage something like this. Here the interesting thing is, you see the pulse width is not constant. The pulse width is changing, right? So you see here the pulse width is small. Gradually it is increasing. At the center it is maximum. And then again it is reducing, right? If you follow the pattern. Similarly, in the negative side also, first this is small, then it is gradually increasing, then maximum here, then again it is reducing. Now here the advantage is, if you filter this out, then you will get a sine wave. So the sine wave is embedded here in the pulses. If you filter out the high frequency components, you will get the sine wave. And here the advantage is, as your switching frequency is very high compared to your fundamental, that's why your filter size is very less. As the switching frequency increases, your filter size reduces, right? So that's why this method is much preferred than the square wave operation, because here you have the embedded sine wave in these pulses and you can easily filter this out to get that sine. Okay, that is the advantage of sine pulse width modulation. So this method is called a unipolar sine pulse width modulation, because here the voltage across the load is either plus VCC or minus VCC, right? There is another method that is called the bipolar sine PWM. There the voltage will be something like this. So there, instead of this, so there will be, the voltage will be like this, either plus VCC or minus VCC. Okay, the voltage will be like this. It will not be zero. Unipolar pulse width modulation is better in terms of distortion. So for unipolar pulse width modulation, you will see that the harmonic content is much lesser than bipolar pulse width modulation. Okay, so I will discuss that in the problem. Okay, so let's go to the problem. Let's see the first problem. Okay, so the figure below shows that a single phase inverter is used with resistive load. The modulation scheme used is also shown in the same figure. Specifications are given: VDC 300 volt, C1 and C2, 2200 microfarad. The load impedance is 100 ohm. Time period is 0.02 second. All switches are ideal. If the sine wave's amplitude is 0.85, sorry, if the sine wave's amplitude is 0.85, then find the peak amplitude voltage between points A and B. So what will be the peak amplitude of voltage between this point A and point B? Okay. So that we need to answer. So here you see they have shown the triangular wave, and they have also shown the reference sine wave, right? This is a bipolar. So when we were discussing the SPWM, you saw that we were using two reference signals. One is like this, another is the inverted sign. for operating these two legs, right? But here they have given only one sine wave. So this is a bipolar modulation. Okay, this is a bipolar modulation because there is a single reference signal. So what will be the switching logic? The switching logic will be uh, like when your reference signal, when your V ref is greater than V carrier, V carrier or V triangular also you can say. Let's see V triangular. That will be easier. So V triangular, right? In that case, S1 and S4, these two diagonal switches will be on, and complementary to that will be S3 and S2. Okay. So when this is higher than this triangular, S1 and S4 will be on, otherwise S3 and S2 will be on. Okay. So in this case, you will not get any zero level. Either the voltage across the load will be plus VDC or it will be minus VDC, right? You can see when S1 and S4, these two switches are on. So suppose at some point of time S1 and S4 are on, right? So when S1 is on, the VDC potential, because this switch is on, so VDC comes here at this point. Okay. And the current flows like this through the load. And again, this is the path, and then through S4, it will come back to the source. Okay. You see the voltage across the load is nothing but VDC, right? Like this. The polarity will be like this. And then the switching logic changes because now your triangular wave is higher than your reference wave. So that's why now S3 and S2 will be on. In that case, the current will come like flow like this through the switch in this direction through S2 like this, right? So you see the polarity changed like this, like this. Now the voltage across the load is minus VDC. If we assume this polarity is positive, then it is minus VDC. So either the voltage is plus VDC or minus VDC. There is no zero level. Okay. So here the voltage, so the amplitude across A and B will be what? 300 volt. Why? Because your VDC is 300. VDC is given 300 volt, right? So you will get a voltage pattern something like this for bipolar. If we are assuming bipolar rear switching, then it will be like this. So gradually it will increase like this, and then again it will reduce. Okay, again it will reduce, just like a sine wave. The sine wave is embedded in the pulse, that's why the widths are like this. Okay, so like this. So the embedded sign will be something like this, and in the negative half also. Okay, but the amplitude is what? Exactly equal to VDC, right? Because it fluctuates between plus VDC and minus VDC. So the amplitude will be 300 volt. But if you want to find out the amplitude of your fundamental, then it will be the modulation index times 300. So the modulation index is 0.85. This is 255. Okay. So modulation index, usually we call it as MA. This is the ratio of your reference signal amplitude, Vref amplitude by your carrier signal amplitude. Okay. That is called the modulation index. So here the modulation index was given as 0.85, right? So, but anyway, that is not like that they have not asked. They have asked what will be the voltage amplitude between point A and point B. That will be 300. Okay. So the correct option is 300. 300. Okay.
Ma'am, what is reference voltage?
Reference voltage is what you want actually at your output. So you want a sine wave, so that is your reference. The same wave that you want actually across your load, that you will give as the reference. Okay, but in a per unit fashion. So they are, so if your carrier is 1, so the amplitude of your reference will be between 0 to 1. Okay, so your MA will be 0 to 1. You want a sine wave, right? In the inverter output, you want a sine wave. So you will give the reference signal a sine wave only. Okay. And whatever frequency you want, you will get the frequency of the reference signal same. If you want a 50 hertz output, then you will give a 50 hertz sine. If you want a 60 hertz output, then the reference signal's frequency will be 60 hertz. If you want 400 hertz, then it will be 400 hertz. Okay, that is your reference signal.
ये capacitor values का there is no use, right? It is just given.
Yeah, they are just given, they are not used. So usually we use the capacitors here. So there will be capacitors, but for this question, they are not required actually.
Okay, thank you.
Yeah. So these capacitors are basically, they maintain the DC link stable for stable DC link, and they also act as filters. So the high frequency components pass through the capacitors. Okay. So, and here you will get a proper DC, ideal DC, and the high frequency components, because you can understand this is a switched circuit. So that's why there will obviously be high frequency components. Those high frequency components will pass through the capacitors, and it will not get drawn from the battery or whatever. Okay, because battery, then your battery will degrade. So from battery you will draw only DC, maybe with slight ripple like this, and the high frequency components will be provided by the capacitors. Okay. Yeah, so next question is, what is the next question? The inverter circuit in question 1 uses the PWM pattern shown in the figure below, in which the reference shown in red is used for leg A and blue one is used for leg B. Then what is the voltage level achieved in one cycle of the reference wave in this duration? So the cycle in the switch in the time period of the reference signal. Okay, so these are the two reference signals. Now instead of one reference signal, we are using two reference signals. So they have asked what will be the different voltage levels that we will achieve in one time period of the reference signal. Okay, so now you see here the switching logic changes a bit, right? Because now we are using two different reference signals for the two legs of the inverter, right? So to operate this leg and this leg, we are using two different reference signals. For leg A, this is the leg A, we are using the red one, and for another leg we are using this blue one. Okay, but the logic remains same. When the reference signal is higher than the carrier wave, the pulse will be high, otherwise the pulse will be low. Okay, uh, and for the blue one also, when this is higher than the carrier signal, the high side switch will be on, otherwise the high side switch will be on off. Okay, these are the high side switches and these are the low side switches. The low side switches always get the complementary signal of the high side switch, Otherwise, the DC bus will be short circuited. Okay, there will be shoot through. So whatever pulse you give to this one, it should be complementary of this one. Similarly for this one also. Okay. So yeah. So you see here. Just a second. So we can see any instances. Okay, then you just observe this intersection point. So if you see this intersection, suppose this intersection, okay, so this intersection where it cuts the carrier wave. Okay, so here if you see the carrier wave is lesser than both the references, right? The instantaneous value of the references here and here, they are higher than the carrier signal. So obviously, both of these switches will be high, right? Just a second, I will. Okay, I will just a minute. I will just copy this one. But here this one is not applicable. Okay. So just this picture I will show. This circuit. So you see during this during this during this interval, both S1 and both S1 and S3 they are on. Why? Because now both the reference signals are higher than the carrier signal. So you can understand the voltage across the load will be zero, right? The voltage across the load will be zero because this is also on and this is also on. Then if you see this small portion, this portion from this point to this point here, the blue one, the red one is high, but where is the, okay, sorry, I think, yeah, sorry. So the red one is lower than the carrier signal. I am talking about this portion, okay, this portion. So the red one is lower than the carrier signal, but the blue one is higher than the carrier signal. So now only S3 will be on, but S1 will not be on. It will be off, right? So then S2 will be on obviously because they are complementary. Now you see the voltage across the load will be minus VDC, right? Because the polarity will be like this. So it will be minus VDC, okay? Then during this point to this point, this interval, both the reference signals are lower than the carrier signal. I am talking about this portion. So now again, both these switches will be off. So again, zero voltage, right? Because now these two switches are on, same thing. And again, if you analyze it, you will get, just a minute. So again, if you analyze at this portion, so during this portion, the carrier signal is low, right? From this one to this one, if you see, the carrier signal is lower than the reference signals, right? So both of them are on again, so zero voltage. And during this period, you see the red one is high. So yeah, so the red one is higher than the uh, okay, sorry, I am confusing you guys. Just a second, I will just make it clear. You understood the logic, right? How this is happening. So if you understand this logic, you will be able to analyze it. Okay. So you just consider all the points where they are intersecting with the carrier signal at all these points. Okay. Then you will be able to understand at this point. Again at these portions, if you see, both of them are lower than this, so 0 voltage. Okay, because none of them will be on. Again, if you see from this point to this point, so you see here this is also high, this is also higher than this one. Okay, so if you analyze like this, you will get that. So far whatever we have got 0 voltage and uh minus VDC voltage, right? We have got 0 voltage and minus VDC voltage. Okay, in these portions. So from here, can you see any portion where we will get plus VDC? Plus VDC means S1 will be on, S1 and S4 will be on, S3 and S2 will be off. Okay. So what will be the condition? So red one will be higher than the reference value, but blue one will be lower than the reference value. Okay. Where can you see it? You see here. If you see this interval, you see, no, sorry, not this one. Can we see anyone where this blue one is lesser than this one, but red one is greater? Mm, I
After
think if we see
0.02.
here, hmm, suppose, uh, mm, just a minute. Okay, okay. Hmm. You were telling at 0.02.
Yes, ma'am.
So at 0.02, so here if you see that at this portion, starting from this portion, so the red one is the blue one is basically higher, right? The blue one is higher, but the red one is lower than this, right? Red one is lower. So here blue one is higher than this, so but then S3 will be on. S3 will be on and red one is lower, so S2 will be on, right? So again you are getting like this negative VDC. So it should be somewhere like this. Yeah, during these positions we will get plus VDC, I guess. If you see here in this range, if you see the blue one is low here, right? At this position. If you follow the blue line, this is blue and this is red. And the carrier signal is this. See here, the blue one is lower than this, but the red one is greater than this. So in this interval, you will get plus VDC, right? So here the objective is you don't have to see for all the intervals. You just have to see a few intervals and you will have to see which voltage levels you are getting. So you are getting 0, you are also getting minus VDC and you are also getting plus VDC, right? So that's what is required. That what will be the voltage levels that you will get. Okay. You see you are getting three levels, plus VDC, minus VDC and 0. Okay. So that's what they have asked. So which one? So the option D is correct, right? You are getting these three things here. So option D will be correct option. Okay. So you don't have to analyze from 0 to till this 0.03 interval. It is not required. Just follow a few instances and see what voltage you are getting. Then you will be able to answer this question. Okay. No need to see all the instances.
And the carrier signal is always high. Then how one becomes
No, this is not always high. Why this is always high?
high? I mean, it is always greater than the reference signal.
No. How? How this is always greater than the carrier signal?
At the peak points.
Just a minute. Just a minute. Just a second. Just I will remove this so that we can understand properly. Oh, this is not good. Anyway. Yeah, so see, the peak of the triangular wave is greater than the sine waves. That is true. But you will have to take the instantaneous values, right? So if you see in these portions from here till this point, this is lower than the reference signals, right? You will have to take instant by instant, not only the peak. So the peak is definitely higher than both of the sine waves. But here if you see this portion, here the negative, it is negative, right? Than these two. This is negative, but these two are positive. Only you just see only during this period. You understood, right? Here it is negative and gradually it is increasing like this. But from 0 to till this point, this red one is positive and this blue one is also positive. They both are having some positive value, right? So that's why the switching logic will appear accordingly. And then again you will have to take all the intersection points. So if you take like this the amplitude, then the amplitude is obviously higher. But if you check every instance like this, then you will see sometimes the triangular is lower than them and sometimes the triangular is higher than them, right? Similarly, in this period, if you see from you see the portions which I am highlighting here and here during these portions, if you see the triangular is negative. It is going like this and it is staying negative and here. But you see the signal, the reference waves are this and this. So obviously they are higher than the triangle, right? You understood, right? What I'm trying to say. So they are higher in this instance, they are higher than the triangular wave. So that's why the this S1 and S3 they will be high. Okay. So it is not about the amplitude, it is about at each instant they will compare whether this is high or the triangular is high.
Yes.
Understood, right?
Yes.
Yeah, okay. Akshit, you understood, right? What I'm trying to say?
Yes, ma'am, got an idea.
Okay. Okay, so yeah, so this is the correct option. Let's see the next question. So in question 2, what is the maximum voltage that appears across any switch during the turn of duration? Okay, so this is pretty straightforward. Yeah. Hmm. So they are asking when any switch is off, what is the voltage that it needs to block, right? So suppose just you can take any instance. So suppose now S1 and S4 this diagonal switches are conducting. Okay. So if S1 is conducting, then S2 has to be off. You see if S1 is conducting, VDC comes here, right? VDC comes at this point. So now S2 is off, this is open. So S2 has to block a voltage equal to VDC, right? S2 has to withstand a voltage equal to VDC. Now the equivalent circuit is something like this. When S1 and S4 are on, these two switches are on, equivalent circuit is something like this. If you see, so something like this. So S1 is on and S4 is also on. So they are like this, and S2 and S3, these two are off. Okay. So these two are off like this. So obviously S2 has to block VDC, and similarly here S3 has to block VDC. Okay. Because they are not blocking anything. The potential is coming here directly. And here, as this is conducting, so this the drain, this terminal is connected to VDC directly. So this will also have to block VDC. So any switch which is not on, that will have to block a voltage equal to VDC, that is 300 volt. Okay. So while choosing the switches, their voltage breakdown voltage should be greater than VDC, the DC link voltage. So I have not written. So this with the answer will be 300 volt. Okay. Whatever is the VDC value, whatever is the VDC value, that will be there. That voltage they will have to withstand. Okay. So let's see the next question. Yeah. This is the controller related question. Which of the following is or are possible Bode plot for PI controller structured as Kp plus Ki by S? Note Kp and Ki both are greater than 0. So you can answer this. Which one is the correct one? This we already saw, right? There is no calculation, nothing. Which option is correct?
D.
Option D, right? The last
Yes.
one.
Yes.
Yes, this is the correct option. Because here, this is not correct because at high frequency, instead of giving attenuation, it is amplifying the high frequency component. So this is definitely wrong. This is definitely wrong. Here also, it is attenuating, but still there is some positive gain. Right, still there is some gain that will introduce noise. So this is again wrong. And this is wrong. Why? Because there is no Kp, and that's why your transient performance will not be good. Right. So that's why the option D is correct. Yeah. So next question is, slope compensation is required for this inductor current waveform, true or false? So this inductor current waveform is given here. So the slope compensation technique we saw, right? That where the positive level and negative level, they don't match, and eventually they get worse. The current, the system becomes unstable as the current is no longer balanced. Okay. So for that we used the slope compensation technique. For this current, do you think that slope compensation is required for this current?
No.
Why? Why it is not required?
No. No mismatch.
Yeah, no mismatch, right? Because this is visible. So see, this is a discontinuous mode of conduction. You see the current is becoming zero, then for sometimes it is remaining zero, then again it starts rising. So the starting point is zero, the end point is also zero, right? We were using the the slope compensation when this level and this level, they were not equal, but now both of them are zero, right? Again it is starting from zero and ending at zero again. So here the slope compensation is not required. Okay. So this is false. This is false. Okay. This statement is false. Yeah. So here there is a question. In the figure below, the asymptotic plot of a PI controller is plotted. What is the value of omega 2? So what is this omega 2 value that you need to find out, right? And this slope is, right? For PI controller, this slope is minus 20 dB per decade. Okay. Minus 20 dB per decade. So can anyone tell how to solve this? So you can pretty much solve this just like a straight line, okay? You just assume this as a straight line and you can have the straight line equation. Think in that way. So suppose this is the straight line, right? How can we find out the slope of a straight line? So simple, what is the simple method? Just the generalized method, that is y2 minus y1 by x2 minus x1, right? y2 minus y1 by x2 minus x1, right? So now you see what is y2? y2 is at this point. This is the end point. This is the starting point. So at y2, what is the value? The gain is minus 20, right? So y2 is minus 20. What is y1? y1 is 30, right? y1 is 30. This is the y-axis. What is x2? x2 is the unknown, that is the omega 2. That is the x2 value. And x1 is omega 1, that is 0.1, right? And we already know this slope is minus 20 dB, right? So this is minus 20. So now this is simple. You have the equation with one unknown and you can simply substitute the values and find out what will be omega 2, right?
31.6.
Right. So 31.62 radian per second. That is the omega 2 value, right? Okay. So yeah. And yeah, while calculating, you should note that these omega values, these also you will have to have in log scale. Okay. So they are in log scale. You understand? So you will have to have them in log scale. Then only you can put this equation. They are not like omega 2 minus omega 1 simply. Okay. They are log 10 omega 2 minus log 10 omega 1. Yeah, so let's see this question. Yeah, so in the DC-DC converter shown below, Q1 and Q4, they are given identical gate drives of duty cycle D. Switch Q2 and Q3 bases are shorted to their respective emitters. Choose the input-output voltage relationship. Okay. So what they are saying that we are giving identical pulses to Q1 and Q4 of a particular duty D. So suppose this is the pulse for Q1 and this is the time period Ts. Okay. So this same pulse we will give to Q1 as well as Q4. The same pulse we will give. Okay. The same pulse we will see. give. So now first suppose Q1 is also on, Q4 is also on. Okay. So you see when Q1, so Q1 is on. Okay. So here there is an inductor. First of all, what you need to understand is whenever they will ask for input output voltage relationship, you will have to apply volt second balance of inductor. If there is an inductor in the circuit, then from volt second balance you can find out V out and V in relationship. Okay, that is the important thing that you need to understand first. Now let's see. Now if Q4 is on, you see then this V minus V out is connected here, right? Minus V out is connected here. So, and another important thing here is you see that these two switches Q2 and Q3, they are gate and emitter, these two are shorted. What does that mean? That means that these two switches will never be on because you have physically shorted the gate and emitter, so these two switches will never be on. However, these anti-parallel diodes can conduct because they are external diodes, so they can conduct, but the switches will not conduct because their gate and emitter terminals are shorted. Okay. So if you when Q1 and Q4 these two switches are on, if you see the voltage across the inductor, okay. So if you apply KVL in this loop, suppose from here to here, then here to here, and here to back to here, okay. If you apply this, then what will be the voltage across the inductor? So first VL, then minus V out, right? Because you are traversing from minus to plus. So minus V out, then from here to here, again minus V in, right? From minus to plus you are going. So minus V in, excuse me, minus V in. So this is 0, okay? This is 0. So what is the voltage across the inductor? Voltage across the inductor is V in plus V out, okay? That is V in plus V out. When Q1 and Q4 are on. Now in the next interval, you are withdrawing the gate pulse. So there is no gate pulse and Q1 and Q4, they are off. And Q3 and Q2, they can't conduct. Why? Because they are already, you have shorted the gate and emitter. So they will not conduct, but these diodes can conduct. So then what will be the path? Then the current can go like this. So current will go like this through this diode, then like this, then through this diode and back to the source. Okay. The current will flow through these diodes. So in that case, if you again apply the KVL, the voltage across the inductor, then what you will get? VL. So VL, it is going like this. So now it is plus V out, right? So plus V out, plus V out. Then it is from minus to plus. So it is minus V in, minus V in is equal to 0. So VL is what? VL is V in minus V out, right? VL is V in minus V out. Now what you need to do is simply apply volt second balance. Okay. To simply apply volt second. So I have described this, the process that I told you here. So if you apply the volt second here, you will get the ratio V out by V in, this one. Okay. So 1 by 1 minus 2t you will get. Okay, so let's see the next question. A boost converter employs current control to control its inductor current. The boost converter has all the specifications: input voltage, output voltage, load resistance, switching frequency L. Does this boost converter require a slope compensation mechanism in the current reference? Okay. So now, first of all, what we will do is we will calculate the duty, because input voltage is given, output voltage is given. You know, for boost converter, V out is V in by 1 minus D, V in by 1 minus D, right? For boost converter. So from here, you can find out what is D. As you will see, the D value is more than 0.5, right? So now you will have to check whether you need slope compensation or not. Okay. So here what we need to calculate is what is delta IL, the ripple. What is the inductor current ripple? So for boost converter, it is V in by L DTS, right? So for boost converter, first let's draw the boost converter. Just a simple, sorry, just so here we have the inductor, and here we have the switch. Here we have one diode, right? Then we have capacitor here, and then we have the load. Okay. So this will be our load terminal. So this is our source voltage V in. The value is given. First, the inductor gets charged through the switch. Okay. So that's why the V in voltage appears across the inductor. The delta L is V in by L DTS. The duty, this is the duty ratio of the switch. So this is this value. Okay. And what is the output current? So for boost converter, the output average and the inductor current average, they are not same, right? Because unlike buck converter, the inductor is in the input side. In buck converter, the output inductor is at the output side. That's why the averages are same. But here the input, the inductor is in the input side. So your output current and inductor current average, they are not same. What is the output current here? We know the output voltage, load resistance. So this is the output current. So in inductor current average is, you can find it out from power balance. So they have told to assume a lossless circuit. So your V9 will be V9 will be V naught I naught, right? For power balance, assuming there is no loss. And you can also find it out by this. So IL average would be I out by D, right? I out by D. In this way also you can find out I out by D. So yeah, so this IL average comes out to be 0.936. Okay. So if you do 3 by 4, so just a second. I will just calculate it and check. 0.234 into 4 divided by sorry, sorry. This is not D, this is 1 minus D. Why? Because you see, like the inductor current free wheels during 1 minus D duration, right? So during DTS duration, the inductor gets charged through this switch, and then we turn off this switch. Now the inductor free wheels and the current flows through the load, right? So that's why the inductor current average is I naught by 1 minus D. So this is 0.936 ampere. What is the ripple? Delta IL by 2, that is 0.937. Okay, if you do delta IL by 2, that is 0.937. Earlier I told you there is a mode called critical conduction mode. What is the critical conduction mode? When inductor current is like this. So it just touches 0 and then again it rises. Okay. So now you see this is your delta IL, right? The ripple in the inductor current, peak to peak ripple, this is delta IL, the current variation from 0 to the peak value. This is delta IL. And in critical conduction mode, the inductor the average current is nothing but the half of delta IL, right? You can see the half of delta IL is the average value. You see here it is coming the critical conduction case. Here delta IL by 2 and the inductor current average, they are same, right? They are same. So that's why the inductor current will start from 0. It will go to the peak. Again, it will come back to 0. And like this, the cycle will happen, right? So even though here the duty is more than 0.5, we don't need the slope compensation technique, right? Because it is in critical conduction mode. So now you saw that even though the duty is greater than 0.5, the slope compensation is not required because it is in critical conduction mode. Okay. So the answer will be the slope compensation here is not required. Okay.
Ma'am, is it critical conduction or continuous conduction mode?
Continuous conduction mode is when your current is like this. Like this. Okay. So in continuous conduction mode, your delta IL by 2, delta IL by 2 is less than IL average. Okay. Less than IL average. That is continuous conduction mode. In that case, your ripple is like this. So this is your del IL. Okay. This is your del IL. And del IL by 2 will be less than IL average. Okay. But in critical conduction mode, they are exactly same because now your del IL is too high and there is discontinuous conduction mode when the current will start from 0, it will come back to 0 and for some time it will remain 0. Okay, and then again it will start. In the last question we saw, right? If you see in which question, yeah, in this one you see this is discontinuous conduction mode. This is discontinuous conduction mode. Okay. Here your IL average is less than delta IL by 2. Okay. It is del, and this is the marginal condition where del IL by 2 is exactly equal to IL average. Okay.
Okay, ma'am.
So yeah. So next one is the multiple choice question. In a closed loop system, the high gain of the proportional controller can cause, you can answer this, right? High gain of the proportional controller can cause what? So the proportional, tell.
Transient.
Yeah, so if you increase the proportional controller, then your transient response will improve. That is one thing. But another thing is, uh, another thing is more noise mixing up with the actual signal that will also increase. Because if you increase the proportional control, then the attenuation will also decrease, right? So your attenuation will decrease. So like this. And suppose your Kp is high, then it could also be like this. Okay, it could also be like this. So so that will also increase. So option D and E, they are correct. Okay. So you have to select this properly so that you can get proper attenuation also and your transient response is also good. Okay, so that is a trade-off. Yeah, and this is the last question. This is an easy one. If a controller is the form of Kp plus Ki by S, determine the steady state error and cutoff frequency. Okay, the cutoff frequency is this one, where so steady state error is zero. Why? Because you are using a PI controller, and for PI controller at DC it gives infinite, it offers infinite gain, right? So your steady state error is zero, and the cutoff frequency is this one, uh, that we already discussed. So where it from where it becomes the slope becomes 0 dB gain, right? So that is Ki by Kp, this one. So this is for 437.5 radian per second. Okay. So yeah, so these are the numericals. So for the next session, that will be our last session. Uh, if you have any particular topic you want to discuss, or you want to you want me to explain in a detailed way, you can mail me or you can tell me now also. Then I shall include those parts. Okay. On Wednesday, if you want any particular topic from previous lectures, then I can explain those things. Okay. So yeah, so thank you for attending. Uh, I will stop the recording then. Yeah,